In this video, we're looking at a static equilibrium problem that's given entirely in general terms. So we have a horizontal rod with mass m. It has a length of L. It's held up at one end by a hinge. And at the other end, it's simply resting on this smooth ramp that's inclined with an angle of theta. In part A, we want to find the magnitude of the normal force exerted on the right end of this rod. And then in part B, we're going to find the magnitude of the force exerted by the hinge. So we get into the force analysis here. And remember, for the purpose of computing torque, we can pretend that the force of gravity acts at the center of mass with a magnitude of mg. Then we have a normal force, so perpendicular to the surface of the ramp, as good as I can approximate that. And then there's some force exerted by the hinge, and it would be nice to have that written into the diagram in the correct way qualitatively. So I think just qualitatively about forces balancing, and I can see a component of the normal force points to the left, which means a component of the hinge force must point to the right. And I'll just call that FHX. And then if I think for a second about torques balancing with respect to the center of mass, the normal force exerts a counterclockwise torque with respect to that center of mass, and this means the hinge must exert a clockwise torque with respect to the center of mass. In other words, the y component of the hinge force is upward. That's probably what your intuition was telling you anyway, but I wanted to be thorough. And so when I put the hinge force into the diagram, I just vector add those two components, and it looks something like that. And we want to find the magnitude of that in part B. So the way we're going to approach part A is by analyzing torques about the hinge. And the whole advantage of this is that it takes the hinge force out of the equations because the hinge force can't exert a torque when the lever arm is 0. And then I say I have a counterclockwise torque exerted by normal force, a clockwise torque exerted by weight, or the force of gravity, and those two must balance. But one thing I have to get done prior to writing anything down is I've got to figure out how to decompose the normal force into its components, so we've got to do a little bit of trig. So here's a quick reminder of some of the trig that pops up in so many of these ramp problems. If I look at the angle between the vertical and the perpendicular to the surface, that's the same as the angle of incline. So that's also theta. We can extend that vertical up here and conclude this angle is theta as well. Then we can decompose the normal force into its components. And for the vertical piece of the normal force, I get an n cosine of theta. This means the horizontal piece, which I'm sure I'll need eventually, is an n sine theta. Then we get into the torque analysis for part A. And again, for this analysis, I'm taking the hinge as the rotation axis. And I'll just write this as all the clockwise torque better add up to the same thing as the counterclockwise torque. Gravity is exerting that clockwise torque, so the force is mg, the length is L over 2, because the force of gravity is attached to the center of mass. And then the counterclockwise torque exerted by the normal force is an n cosine theta acting through the entire length of the rod. The L's are going to cancel here, and I find that n, the normal force, is going to be mg over 2 cosine theta. In part B, I want the magnitude of the force exerted at the hinge, and I can get this done by looking at the sum of the forces in the x and y directions. So there's only two forces with x components, and that's the normal force with a leftward component and the hinge force with a rightward component. And those x components must balance. So just comparing the magnitudes here, n sine theta is the leftward force on this rod. That better have the same magnitude as FHX, the x component of the hinge force. In terms of the given variables then, the x component of the hinge force is n times sine theta, so I take my answer for n from part A and I multiply by sine theta. And then I notice I have a sine theta over cosine theta, so I could rewrite this as an mg over 2 times tangent theta, or it might be nicer to write it as a 1/2 mg tangent theta. Then I do a y analysis to figure out the y component of the hinge force. So all the forces pointing up on this rod better add up to the same thing as all the forces pointing down. So I have the hinge force in the y direction. I already established qualitatively, I know it points up. Plus the vertical component of my normal force, that's an n cosine theta, has got to be equal to mg pointing down. Well, if I look at n cosine theta, going back to the result from part A, that would be mg over 2, because the cosine thetas will cancel out. So I get FHY plus mg over 2 is equal to mg. I subtract 1/2 mg from both sides, and I find out the y component of the hinge force is simply mg over 2. And then the goal of this problem is to figure out the magnitude of the force exerted by the hinge. Well, now I have the x and y components, and I can get the hypotenuse, the magnitude of that hinge force, by using the Pythagorean theorem. I'll go over to the left to do this because it takes a little bit of space. So my hinge force magnitude is given by the square root of the sum of the squares of the components. I plug in my components, and I see that they have a common factor of mg over 2 in them. So this is a common trick. I can pull the mg over 2 squared out of each of those terms and then pull it out of the square root, giving me just an mg over 2. What's left over in the square root is a tangent squared theta plus 1. But tangent squared theta plus 1 is just secant squared, and when I take the square root of that, I'm left with mg over 2 times secant theta, which, by the way, is the same thing as my normal force magnitude. That's mg divided by 2 cosine theta. And it doesn't surprise us, given the symmetry of this problem, that the hinge force ended up with the same magnitude as the normal force. But I wanted to show the solution in a completely general way, so hopefully you're better prepared for a problem that has less symmetry in it. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.